Hey girls, so I still wanted to give y'all a little bit of our class today. So this is my best shot today. Anyway, so this chapter is all about minerals, which are the substances that make up rock. So I've got several different examples here. And we want to kind of go through and look and see if these are minerals or rocks. So we've got some green calcite and some obsidian. That's this one. We've got some graphite, sphalerite from Wisconsin, and some sulfur from Texas, and then we got some mica here. This one came from Wisconsin too. That one's all the way from Mexico. And these are some actual samples of rocks that I collected over the summer. So let's look at them. Two of them are rocks and the rest are minerals. So what is the difference between a mineral or a rock? So minerals here are very similar to pure substances, where our rocks are always a mixture. Rocks can have more than one mineral in them, where a mineral is a mineral is a mineral. So looking here, let's look at this calcite. So if we focus the camera on it, I see that it's got this nice little square shape. Ooh, that's got a pretty little seam running through it. And it's mostly, let's see if I can get it to focus. There we go. It's mostly green, right? So this one looks like it's made of the same thing. It's got this nice rigid structure. This one is a mineral. This one is graphite. Or sorry, granite, like a countertop, right? It's not smooth. If we were to pick it up, it's very rough. I see lots of different colors in there. I don't see just one stream of color that's some impurities. It's definitely not got a fixed composition. This one is a rock. Let's see right here. This is our sphalerite. Looking at it, it's real shiny. If you can see it, it's got some really flat pieces to it. It looks like it's made of all the same things. So there's this big impurity on the side. So it's another kind of rock in there. But this sphalerite is actually a mineral too. Compare it to the granite, right? It's all kind of the same thing. If I can get my camera to focus. It's all kind of the same thing. Ooh, there we go. It's all kind of the same thing. Whereas this granite over here has all different kinds of things in it. So sphalerite, mineral, granite, rock, calcite, mineral. Our obsidian down here is kind of the oddball. So if we look at it, it's really solid. If we were to crack this open, it would look very similar to our calcite. See how the calcite's very cubic, very shiny. Our obsidian is like that too, but our obsidian is actually rock. It's a metamorphic rock, so it came from some lava, some magma that cooled down. And then we've got this mica here. If we pick it up, I don't want to pick it up because it's really, really thin. Oh, look, you can see straight through it. It's transparent. It's really, really thin, right? You can see my fingers there, my awful cuticles. It's really, really thin, and it's transparent, right? So this mica right here definitely has a fixed composition. It's the same thing. It's not a mixture like our granite. So what do you guys think this one is? Hopefully you're saying to yourself in your head that this is a mineral, because it most definitely is. Oh, and look how that reflects right there. It's kind of shiny. Okay, and then our sulfur over here is nice and yellow. It also has a fixed composition, so it is also a mineral, even though this is a mostly pure sample of sulfur. If we were to smell this, it would smell a little bit like rotten eggs. Okay, cool. So hopefully you got from that our minerals have a fixed composition and are closer to a pure substance than rock, which is a mixture, can be multiple different minerals. Our mineral being our basic smaller unit here. And we see those examples. So let's bring that out. So you can see all of them together. So that's the first part is a mineral or rock. So once we know what a mineral is, it's our kind of basic unit of the crust, since we're studying about the Earth's surface. Now we're going to look at more specific qualities, how we can tell one mineral from another. And we're going to use our samples here to kind of go through this list. So most of the whole rest of your chapter is talking about the properties of minerals. So just like elements have physical and chemical properties, so do minerals, because minerals are just this kind of mixture of elements chemically combined. So the physical properties can be subdivided into kind of three categories. We've got optical. These are all how light behaves with the mineral. So we got reflection, so that's the color. We've got reflection too, because that's a streak. So it's when we ground it up into a powder, what color is it? We've got its luster. This is how it reflects light, if it's shiny or not. And then we've got transmittance, and that is how light can pass through our mineral or if it can't, right? So this is where we have our transparent, opaque, or translucent. And then we've got our mechanical properties. So this is how our rock feels, how it breaks apart, how hard it is. So the hardness. We've got if it fractures, is it crumbly? Or does it cleave? Does it break apart into these flat, smooth surfaces? If it doesn't break apart into flat, smooth surfaces, how does it fracture? How does it break apart? Is there a pattern or is there not a pattern? It kind of, like I said earlier, crumbliness. And then we also have this kind of weird category of magnetism. So some objects are diamagnetic. They can repel a magnet regardless. We have paramagnetic things, which have a slight attraction but can't be turned into a magnet. And then we have ferromagnetic materials, which are very attracted to a magnet and can actually be turned into a magnet if they're exposed long enough to a magnetic field. Then we also have our chemical properties. So they tell us the elements that make up the mineral, and we can react them, and some of them react with an acid, and that's called effervescence. So the whole rest of our chapter talks about how we use these properties of minerals to identify them and use those minerals. So I want to go through a couple of our samples over here and talk about each of these properties. So let's observe the calcite first. So we've got the calcite here. Let's go through its optical properties. So obviously color. I see that thing is mostly this really pretty, and let's zoom in on it. Mostly this really pretty green color. It's got a streak of some impurity in there, or some other type of mineral, or sorry, some other chemical in there. So the calcite, we'll learn in just a minute, can be, it can have a couple different chemical formulas. So we might have two different types of calcite within this one sample. But it's definitely got this greenish gray look to it. For its streak, if we were to take this and rub it on a tile, it's going to give us this nice grayish powder. So that green color, you kind of lose once you grind it up. So it's going to be a gray kind of powder. That's what streak is. And luster is how this thing reflects light. So if we look at it, there's definitely part of this that's kind of shiny, that white kind of iridescence. But this is definitely not a metallic luster. It's not shiny all over. It's just got some parts that reflect a little bit of light. So this would be a non-metallic luster. And you can classify non-metallic lusters like pearly or silky. This one I think would be pearly. And your book lists several other different types. So that's luster, how it reflects the light. Is it shiny like a metal, or is it not shiny? This one is not shiny. This one would have a metallic luster. This one's our sphalerite. You see how it looks very metallic. It's very iridescent. You see all those little facets on there. That's a good angle, right? So this one would have a metallic luster. Okay, so that was luster. And then we've got transmittance. So light can pass through this one. This one is translucent. If I were to shine it up to a light bulb, you would be able to see that light through this, but it wouldn't be a clear picture. So that would be translucent. Our mica over here is transparent. You can read that through this mineral. It lets light pass completely through. But then we've got our sphalerite. it reflects all the light. It doesn't let any of that light pass through. It is it's opaque, sorry. I was gonna say it's transparent. It's not transparent. The mica is the transparent one. All right, we can go all the way through. So we've got here our example. So this one is our opaque. This one was our translucent. This one was our transparent minerals. Okay? Now, we want to talk about our mechanical ones now, cleavage. So cleavage is how our minerals cut apart. So this one has a very crystalline cleavage. It has a high degree of cleavage. You see, it cut apart in these very rigid, sharp planes. You can definitely see here. It's almost like square, right? And see how smooth and flat that surface of that rock is? That's natural. This thing has not been sanded. It has not been ground down. It broke apart. It fractured into these perfectly flat surfaces. That's called cleavage. So this one, our mica here, also has cleavage. See how smooth and flat these surfaces are? So this mineral cleaved into these, along these perfectly flat edges are lines, based on the structure, how those molecules are actually put into there. Now, our sphalerite over here, we don't see that. This piece of sphalerite, well, you can kind of see it's got a couple of little cleavage planes, but they're not, that is definitely not as flat nor as smooth as our other minerals that I just showed you guys. So this one does not have that kind of degree of cleavage. This one is an example of fracture. This rock has fractured. It has not separated and cleaved into these perfectly flat surfaces. It doesn't have lines of cleavage. This one does not have those lines of cleavage. It's more of a fracturable type of rock. And that comes in how the atoms are hooked together. And then we have hardness. So you can actually measure some of these minerals are harder than others. Typically ones that have cleavage are harder than the ones that fracture. So we could test this. So we could take a nail or different hard substances and try to scratch all of these. And there's a scale. It's a number 0 to maybe even up to 13 of how hard these minerals are. Sulfur is not very hard at all. You could probably crumble this with your hand if you tried hard enough. What about our mica? Do we think our mica is easy to crumble? Yes, it is. Like I can even see this part. See, a little piece just crumbled off. So this one is not very hard at all. Whereas our calcite is harder. I think the hardest one we have here, since those are rocks, is probably the calcite. Anyway, so the only way you can determine the hardness of a rock is to try to scratch it with something or make it break. That's the only kind of way we have to measure or quantify how hard that mineral is. And then we've got our magnetism. Of all of these, I believe that our sphalerite is the only one that is paramagnetic. All the other ones are non-magnetic at all. And then some minerals are diamagnetic, so they will be repelled by any kind of magnetic field. The only one that I know about, and your book mentions it, is graphite, which is what's inside of our pencils. So that's a mineral, graphite, inside of your lead pencils. Who knew? You use minerals every day. And then we have to talk about our composition. So with the composition of our minerals, their composition, I told you earlier, was fixed. And that's not necessarily true. Minerals are more like a family. So like where we saw this calcite, it's got streaks in there. It's got those streaks in there, right? So the chemical formula for this guy looks really, really complicated because there are several different versions of each of these minerals. It's like a family. So this is green calcite, there's purple calcite, there's white calcite, all different kinds, and that has to do with its chemical formula. So your book, your comprehension check question, has this as a chemical formula for hornblende. So we can see here that there's some parentheses. there's two sets of parentheses. This parentheses over here is, there's not an option, there's not a comma. So this OH right here is OH. It's peroxide or a hydroxide group. And it's got this 2. So this 2 right here tells us there is 2 of whatever is inside our parentheses. So this thing on the end has 2 O's and 2 H's stuck on it. It's got H silicones and 22 oxygens. So that means that it's a silicate because it's got silicone and oxygen. And then we see this parentheses. It's got a comma in between iron and magnesium. So this mineral, this hornblende right here, I keep calling it horseblende, this hornblende can actually have 2 different chemical formulas. It can have the Ca2, Fe5, blah, 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 or it can have Ca2, Mg5, blah, 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 blah. It's kind of got 2 options in here that we see in nature that can make the same mineral that has very similar properties other than probably color. Might have a little difference in fracture but based on the size difference between each of these pieces, but it's still generally going to be the same hornblende family of mineral. So, how do you tell the difference between the parentheses if it can be a different chemical formula? You look for the comma. If we see a comma here, then that means it can be either of these, not both of them at the same time, either one or the other in a different type of that mineral. Okay, so we've got another question I want to talk about before we move on, and that would be this question right here. There's a mineral group called augite. One member is MgSiO3. Which one of the following would be a different member of the augite group? So we want to look at this ending right here. This is a silicate, right? It's because it's got silicone and oxygen. So this is the part that can't change within that family. This is kind of like the recipe for that. So we want to find something else that has a different metal stuck with this silicate ending, SiO3. So looking down here in my options, I only see one that has the same ending as my MgSiO3. This one doesn't. It has Si3O8. It's a different family of silicate. This one has SiO3, but this one's got iron instead of magnesium. This one is the other member of that augite family. This one can't be because it's only got 2 oxygens. This would be a different type of family. Okay? Cool. And then our question down here, we want to look for the ones that don't have silicate, so the ones that don't have silicone and oxygen. Obviously, this one is a silicate, SiO2. It's got silicone and oxygen. Copper is just a metal, so that will be there. We've got FiSiO2. I see silicone and oxygen. Bingo, it's a silicate. I see S and O4. That's actually not silicone, that's sulfur. So this one is a sulfate, calcium sulfate. This one is potassium chloride. I don't see any silicone and any oxygen, so it's not a silicate. It's actually a salt. If you have people in your family who can't eat regular salt or on a low salt diet, this one is potassium chloride. It is the salt substitute for people who can't have table salt. And then we have AlO3. This is aluminum oxide. It is also not a silicate because there's no no silicone and no oxygen paired together. Hopefully that helped with your questions on minerals and how to interpret them. The only other things left in the chapter that you'll be reading about the rest of the week are how our minerals form. You could actually, looking at this picture here, if you've ever made rock candy before, you can totally make rock candy. It's just allowing those crystals time and space to come together and orient and make these beautiful structures. Some minerals are able to have beautiful structures like this, and some, based on how they're able to form, don't have this nice, beautiful, rigid structure. But we can manipulate them in the lab to have these beautiful structures. That's how we have lab-created diamonds and lab-created sapphires and all these beautiful gemstones. They're just minerals that have been treated and grown in this kind of controlled environment, not like you would see in nature. Most of them form slowly through precipitation. So water carries away in erosion or weathering, or erosion paired with weathering. And that water slowly evaporates, or like in a cave, drips down and leaves the minerals behind. Or we could have magma come up out of the Earth's surface and cool off. That's actually how we get the minerals formed in this obsidian. If I were to cut this open, let's see the picture. It's in your textbook. If I were to cut it open, well, that's the galena. There's a picture of obsidian in your book. Oh, I guess we can use this picture. So this would be like our gemstone. So this is what we would get in the real world. But if we polished it and ground it down and slowly fractured it in specific ways, we can actually turn this into that. And that's what gemologists do. That's how diamonds are created in this beautiful kind of faceted ways. Diamonds look like this in the real world. They don't just pop out of the earth looking beautiful and would be fit right into a ring. Our people, scientists, whatever you want to call them, spend lots of time polishing and cutting our stones and cleaving them along these surfaces. So, there's that. Here we have another example. So this is an amethyst. It's actually my birthstone because I'm born in February. And they can turn this into that. This is one solid piece of gemstone. And then there's some examples of how you can do a unit conversion to figure out grams into how big a carat you can make of a gemstone. But hopefully this kind of equation will be very easy for you because you know how to do unit conversions. We know that our 1 carat is 0.2 grams, so I can take this equivalent statement and I can turn it into a fraction based on if I start with grams or if I start with carats. Because I could ask you also, a 5 carat gemstone will weigh how many grams? And if you know this conversion factor here, you should be able to figure that kind of equation out as well. So I hope this helped you guys out. I'm sorry that I couldn't be there for a live class today, but we will find a time later. If you guys need one-on-one help, I don't mind meeting with y'all later on this week when I'm feeling a little better. But hope y'all have a good rest of your day.